OOP is a topic that is repeated year after year in all technical universities around the world. If you have just started your studies, this topic will be helpful for you shortly. What is OOP? Object-Oriented Programming, OOP, is a computer programming model that organizes software development around data or objects rather than functions and logic. An object can be defined as a data field that has unique attributes and behavior. This paradigm focuses on the objects developers want to manipulate rather than the logic they need. This programming approach is well suited for large, complex, and actively updated or maintained programs, including manufacturing and engineering programs and mobile applications. For example, OOP can be used for manufacturing system simulation software. The organization of an object-oriented program also makes this method useful for collaborative development when projects are divided into groups. Additional benefits of OOP include code reusability, scalability, and efficiency. In object-oriented programming, we think of programming as an interaction between objects. When we create an object, we specify the type of object, the types of data it will store, and the types of operations it allows us to perform to manipulate the data. However, it hides its implementation from the user, meaning we cannot look under the hood of our code. Imagine you own a car. In object-oriented programming, a car can be represented as an object of class, car. This class will have properties such as make, model, color, etc., and methods that define its behavior, such as start engine, move, and stop. Let's say you have several cars of different makes and models. Each will be a separate object of this class, car. You can interact with each vehicle independently of the others by calling its methods or changing its properties. Thus, object-oriented programming allows us to model real-world objects and processes, making our code more understandable and easier to maintain. Let us now briefly run through the basic principles of OOPs. Encapsulation. This principle states that all critical information is kept inside the object, and only selected information is displayed outside. The implementation and state of each object is stored inside a particular class. Other objects do not have access to this class and cannot be changed. They can only call a list of public functions or methods. This feature of data hiding provides more security to the program and avoids accidental data corruption. Abstraction. Objects reveal only those internal mechanisms that are important for use by other objects, hiding unnecessary implementation code. A derived class can extend its functionality. This concept helps developers make it easier to make additional changes or additions over time. For example, if we have an ATM class with a withdraw cash method, we can call that method without knowing exactly how it is implemented. This makes it easier to develop and maintain a program because we can change or improve the internal details of the class without changing the code that uses it. Inheritance. Classes can reuse code from other courses. Relationships and subclasses can be established between objects, allowing developers to reuse common logic while maintaining a unique hierarchy. This property of OOP allows for more thorough data analysis, reduces development time, and provides higher accuracy. To get a better understanding, let's look at a mom and daughter example. Let's imagine we have a class called Mom, which has unique characteristics and skills such as cooking a delicious dinner and saying hello. Now, let's imagine that we have a class Daughter, which inherits all these characteristics from the class Mom, but also has its own, such as the ability to study and a unique way of saying hello. So, in our example, Daughter inherits from Mom not only the ability to make dinner and say hello, but also adds its unique characteristics, such as learning and a unique way of saying hello. Polymorphism. Objects are designed to behave together and can take more than one form. A program determines what value or usage is required for each execution of an object from the parent class, reducing the need for code duplication. A child class is then created that extends the functionality of the parent class. Polymorphism allows different types of objects to pass through the same interface. Let's imagine we have a class called Person that uses a behavior method to determine how a person behaves in different situations. We now have two subclasses of this class, student and customer. Both of these classes also have a behavior method that describes their actions at the university and the store respectively. The behavior method for student can output studying at university. The behavior method for shopper can output buys groceries at the store. That's how this example demonstrates polymorphism. Same behavior method, but different implementation for each subclass depending on the context. But why use an OOP? What are the advantages? One of the main advantages? We can highlight such points. Modularity. Encapsulation allows objects to be self-sufficient, which makes troubleshooting and collaborative development easier. Reusability. Code can be reused thanks to inheritance, which means a team doesn't have to write the same code multiple times. Productivity. Programmers can create new programs faster using multiple libraries and reusable code. Easy modernization and scalability. Programmers can implement system functionality independently. Interface descriptions. Descriptions of external systems are simple due to the message passing techniques used for object interaction. Security. Encapsulation and abstraction can hide complex code, simplify software maintenance, and secure internet protocols. Flexibility. Polymorphism allows a single function to adapt to the class in which it resides. Different objects can pass through the same interface. But there is a flip side to the coin. Developers have criticized the object-oriented programming model, OOP, for many reasons. The biggest concern is that OOP emphasizes too much data in software development and not enough computation and algorithms. In addition, OOP code can be more difficult to write and take longer to compile. Alternative OOP techniques include functional programming. This includes languages such as Erlang and Scala, which are used for telecommunications and fault-tolerant systems. Structured or modular programming. This includes languages such as PHP and C#. Imperative programming. This alternative to OOP focuses on functions rather than models and includes C++ and Java. Declarative programming. This programming method involves formulating a problem or desired outcome, but there needs to be a way to achieve it. Languages include Prolog and Lisp, logic programming. This method, based mainly on formal logic and using languages such as Prolog, contains a set of sentences that express facts or rules about a problem domain. It is oriented toward tasks that can benefit from rule-based logical queries. Most modern programming languages allow developers to combine models because they can be used for different programming methods. JavaScript, for example, can be used for OOP and functional programming. What are some examples of object-oriented programming languages? Although Simula is considered the first object-oriented programming language, OOP, many other languages use OOP today. However, some programming languages combine with OOP better than others. For example, programming languages that are considered pure OOP treat everything as objects. Other programming languages are designed primarily for OOP, but with some procedural processes. For example, popular pure OOP languages include Ruby, Scala, Jade, Emerald. Programming languages designed primarily for OOP include Java, Python, C++. Other programming languages that work in tandem with OOP include Visual Basic.NET, PHP, JavaScript. Today, we briefly reviewed the main points of OOP, breaking down the basic idea and deciding when to use it. However, this is only a tiny part of what I want to tell you. There are many more exciting things we didn't cover today, such as why encapsulation is not just hiding data, whether to use inheritance, and to what limits to use abstraction. The following videos will cover all these topics, but in the meantime, review again, take notes on the main points, and practice. Only practice will help you better understand and consolidate the material you have learned.